Now that we know to very easily change the basis of a matrix, suddenly a whole world opens up to us, okay? So we were always trapped in the x hat, y hat basis, but now we can choose to write whatever matrix we want in whatever basis we want, okay? And there is one particular choice which makes things very simple for us and can be very useful, and that is the main application of eigenvectors. And that's called the diagonalization of a matrix, okay? So in order to understand diagonalization, we need to understand the concept of an eigenbasis, okay? An eigenbasis. So let me write it down. When the eigenvectors of a matrix are linearly independent, and they span the whole space, then this means that this set of vectors can be used as a basis, right? We can use them as a basis. Remember, any set of vectors that are linearly independent and that span the whole space can be used as a basis for that space. So when we do that with the eigenvectors, because they are linearly independent and span the whole space, we can use them as a basis, and this is called an eigenbasis. And when we change the basis of a matrix into this eigenbasis, very special things happen. Spoiler, the matrix becomes diagonal, but let it see an example. So let's do it with an example. So consider the following matrix: m equals 5 minus 2, 2, 0. If you calculate the eigenvectors and the eigenvalues, you get these two eigenvectors with these two eigenvalues. And you can see that the eigenvectors are clearly not parallel to each other, and they are two-dimensional, so they are linearly independent, and they span the whole of the 2D space. So we can use the eigenvectors as our basis, okay? So do a change of basis so that we use the eigenvectors as the basis. So let's do it. So our old basis is x hat and y hat. And our new basis is going to be v1 and v2, which is equal to 2, 1 and 1, 2. Okay? So this is going to be our new basis. So our change of basis matrix so A is going to be v1 and v2 placed as the columns. Remember that, right? And they are placed as column vectors written in the old basis. So indeed, the vectors 2, 1 and 1, 2, they are written in the x hat, y hat basis, because that's the basis in which the original matrix was written, and that's the basis in which we calculated the eigenvectors. Okay? So they are already written in the x hat, y hat basis. Let's write it down. Written in x hat, y hat basis. So therefore, our change of basis matrix is going to be equal to 2, 1, 1, 2. That is going to be the change of basis matrix associated to the eigenbasis of this matrix. Now, we will also need the inverse, as you know, yeah? So the inverse is going to be 1 divided by the determinant of A times dA minus B minus C, where I used the typical notation where the original matrix is A, B, C, D. And this is equal to the matrix, let me write a prefactor of 1/3 of 2, minus 1, minus 1, 2, because the determinant is 3. Okay, so this is the inverse. So now we are ready to change the basis of the matrix. So change basis of M using the similarity transformation. So M prime is equal to the inverse of A times M times A. So this is equal to 1/3 2 minus 1 minus 1 2 times M, which was equal to 5 minus 2 2 0, times A, which is equal to 2 1 1 2. So now we do this product here. I won't spend the time doing it, but you already know how to do products of matrices, and the result is 4 0 0 1. The matrix that results when we change the basis into the eigenbasis is a diagonal matrix. Diagonal matrix means that the only elements that are not 0 are the elements in the main diagonal. Diagonal matrix. And not only that, but notice that the values of the elements of the diagonal coincidentally are equal to the eigenvalues associated to each eigenvector, right? Is this a coincidence? Well, no, this always happens, and it's always the same, okay? So let me explain why. Why does the matrix become diagonal when you write it in the eigenbasis? So let's remember back to the first part of matrices, when we were learning how to write matrices as linear transformations. So the matrix M represents the linear transformation M applied to x hat, and that was the first column of M. And then the linear transformation M applied to y hat, and that is the second column of M, right? And this is because we were using the basis x hat and y hat. But now if we are using the basis v1 and v2, we can apply the same logic, that our matrix M prime in the new basis has a first column, which is the transformation M applied to v1, and the second column will be the transformation M applied to v2. In general, if we were in n-dimensional space, this would just be v1, v2, v3 up to vn, corresponding to the n eigenvectors. Yeah. So this is in the eigenbasis v1, v2. But now I ask you, what is M, the transformation applied to v1? Well, the transformation applied to v1, by definition of an eigenvector, if v1 is an eigenvector, this is equal to the eigenvalue multiplied by v1. Okay? And this is equal, you can write it as a linear combination of v1 and v2. This is lambda 1 times v1 plus 0 times v2. And if we had n eigenvectors, it would be plus 0 times v3 plus 0 times v4 plus 0 times vn. So it would be written as a vector that is lambda 1, and then the rest is all zeros. Okay? In the basis v1 and v2. So in this basis, this vector is written like this. Yeah? What about the transformation applied to v2? Well, obviously, v2 is an eigenvector, and the eigenvalue is lambda 2. And this result as a linear combination of the eigenvectors, which are the basis, is equal to 0 times v1 plus lambda 2 times v2. And if we had more eigenvectors, it would be plus 0 times v3 plus 0 times v4 plus 0 times vn. Yeah? So if you write it as a column vector in the basis v1, v2, this will be zeros everywhere except on the element corresponding to the vector. So the second element in this case will be lambda 2. Okay, and therefore M prime is just putting these two columns in this basis, so it will be lambda 1 0 0 lambda 2. So it is a diagonal matrix, and the values of the diagonal are equal to the eigenvalues. In general, for n dimensions, n prime will be equal to lambda 1, lambda 2, up to lambda n in the main diagonal, and zeros everywhere else. Okay, it will be a diagonal matrix with the eigenvalues along the main diagonal. So this means that any matrix that has an eigenbasis associated to it can be rewritten using this eigenbasis as a diagonal matrix, which kind of makes the matrix really simple. Okay? Excellent. And what can we do with this? And some definitions related to this, we will study this in the following videos. Thanks for watching.